Hi. I haven't given talks in years, so this is a little bit of an experiment today because I will not talk so much about science, but actually more about, it's an opinion talk about software. Okay, so it's already starts well. I want to talk about, as the title says, how to simulate molecules, and I guess here in Berlin we have a lot of people interested in that, with all the MD work at Fritz Haber Institute, the people at FU and so on. But the time of AI, fancy buzzword like we know it, like machine learning, changes a lot of this. And I want to talk a little bit about what we do at CuspAI in the beginning, but also lead over into how all this disruption that's happening now ties into our work, how we answer that in-house with a certain tool that's published. And then from there, this is the opinion part, what my perspective on this is for the future of any kind of simulation software development and even more. So just quickly about CuspAI. So this is our logo and our website where you can find us. We are basically working on materials for a better world. And what do we mean with that? Concretely, we mean something like perovskite solar cells. We try to just get more energy out of a same square meter of a solar cell. Then we look into polymer fuel cells with partners. We are looking into semiconductors in general, like manufacturing, optimization, making it less toxic and so on, and a lot more. So what we do here is basically we build a search engine, or like you could say an inverse design engine, which is mostly driven by an agent. And it uses a huge cascade of different tools on all stages of the simulation. And the idea here, so that's our main pitch, we wanted to turn the usual decades of work that flow into that into months. And we do this with very close partnerships with companies working on this, national labs working on this, and so on. So now at the core of all of this vision is an agent operating software. Because in the end, we know there's a lot of stuff that, where we basically cannot really hope that an LLM will just spit it out of the box. So big question, and this is the provocative one, why do we still build software? And here I just want to give you some quotes. So this one is from Jensen Huang from NVIDIA, which is just paraphrased, but basically nobody has to program anymore. You just use natural language. Why would you even start programming as a kid, right? And another one, Dario Amodai, AI writes 90% of the code. This was a year ago. So I guess now maybe 99%, whatever. And this is like a most funny one. This is something I got at NeurIPS from an anonymous Anthropic researcher who literally said, isn't Cusp just a cloud wrapper? So I want to dive into this a little bit, kind of as a provocative ask in the beginning, to actually lead over to why I don't think so. So today's talk, first part is I want to talk about a real problem that we tackle at Cusp. So not just make something fake up, just something that we actually work on. How that actually led to building a new tool, so new software, not a machine learning model that feeds it all, but really new software. And then the bet that, at least for me, is behind this and led me to designing it the way it is. So let's talk about the real problem, climate change. So as we all know, we have a problem. We need to get rid of CO2. And the most obvious one is to just not emit it. But then the maybe less obvious one is there's good reasons to also suck it out of the air. Problem is we have to scale it. And so here these are just some, basically bulletin estimates of like, if you look at the usual net zero plans, then there are like a lot of negative emissions already priced in, where people just hope we will be able to do them. But you can see the scale up phase is quite immense. And we are still on the very left side of this chart. So how do we get there? And one big promising idea is direct air capture, where you hope to just in chemical industry scale capture CO2 from out of the air, basically. And now the cost of this is set by the sorbent, so the material that captures the CO2, and then if you want to recycle it, has to release it again. And it's clear, the cheaper you make these materials, the closer you get to your goal. So you could basically see it as a cost chart, the usual ask and bid price. So if we get better materials, we actually move the viability to the left. So the earlier the society is willing to pay for it, the earlier we get rid of the problem. Now the question is like, which is the material here that is a hot candidate? And the name is very fancy. It's metal organic frameworks, short MOFs. So what is it? So meta-organic frameworks are basically you take metal nodes, which are like atoms, and organic linkers, which are like short molecules that think about them as a stick. And then if you put them together in the right conditions, that's the hard part, they will self-assemble into so-called porous structures. So think about them basically forming a molecular sponge where the atom nodes are on the corners and then the linkers connect them into this kind of grid. Yeah, and these materials, they got the Nobel Prize last year in chemistry. It's kind of materials Lego, because now you can play around which atoms you pick for the metals, but also which linkers you add to that. And there's billions of combination, nice blow up. And they're ideal for GetDAC, mostly for the reason because they are cheap to produce once you found them. You can scale them heavily, you can reuse them. So basically tree material for the task. Question is then, if you have so many choices, what's a good one? And there are like some hard criteria. It shouldn't be toxic. I mean, if you use gold or whatever, then of course it becomes very expensive. So there are like a bunch of obvious choices. But even in the smaller space of MOFs where you say they are suitable, question is like, what is a good one? And one criteria that's actually not so tricky to determine, but it's also something that you can address with computation is the question, how do we make it catch CO2 in these pores, but not water, not nitrogen, which is a lot more in the air. So there's more water in the air right now than CO2. So how do we get this little tiny CO2 that's in the air in the MOF? So just a visualization, we want to have it in and keep the other stuff out. So yeah, the question is a little bit like, once we are in this stage and it's full, of course, how do we reuse it? So we have to kind of reset the filter, otherwise we have to throw away a lot of toxic waste. The idea here is, and that makes MOFs ideal, once this bound in the pores, we can just use pressure or temperature and then release everything in a controlled atmosphere where we then suck away the CO2 and, for example, press it down on the ground. Question is now, how do we select now a MOF that satisfies this? And the idea here is the so-called isotherm. So that what you basically say is how much of X could be CO2, could be water, could be nitrogen, is captured at a given pressure. And this is a partial pressure of the gas and a given temperature. And then, for example, if you plot this, then you get like on the left, for example, prototypical curve for CO2. On the right, you get one for water. And then by basically profiling these different curves, you can then screen candidates where this is as separate as possible. And then for like the conditions at hand, you can then make the cut where you say this is a MOF specifically for this environment that will operate the best. Question is like, how do we compute these curves? And this has this fancy name, Grant Canonical Monte Carlo. So what it is basically you throw things at the wall and hope what sticks. So what you do, you have this MOF, you basically put it into a reservoir. This is like some chemistry thing that you make up, and basically then set the temperature and the pressure, and then you try with Monte Carlo to insert CO2 into the pores and move them around. Sometimes they get accepted, sometimes they get rejected, and over time you get like a curve that estimates the average loading. And from that you can estimate, basically where you are on the curve given the pressure. So what's the challenge with it? A lot. So first thing, we have one run. So Monte Carlo sequential, so we have like a one run with thousands of little MC steps. The question is, in the isotherm, you have a lot of these runs. So one of them, already many MC steps, they are all sequential because you need the last pressure point to compute the next one. And then the problem is like one material is usually a surface of different mixtures. So because a gas is not just one gas, it's like a mix of different gases. And then of course you have tons of materials to screen. And if you zoom in the question of the mixtures, it's already very interesting, because if you look at, for example, different conditions, like you have a dry condition and you say it's mostly nitrogen and CO2, then it's maybe easy. But once you go to more humid conditions, these profiles totally change. So it's actually sampling from a big hypersurface, blowing up the combinatorial space even more. And then there's the last problem that I want to mention here, because it's tricky. Water is a special one. And the reason for that is water forms these nice networks with van der Waals bonds between the hydrogens, which is super interesting and sometimes captivating to observe. But the problem is then if you have an insertion and you do just a knife insertion, then most of that will just be rejected, just because it needs to really fit into these hydrogen bonds. And this is something that the classic tools really don't capture well. So usually, as I guess it's an AI conference, so machine learning to the rescue. So if we basically use machine learned potentials, and I guess here in Berlin, many people know about this. It's one of the hotspots in the world for this topic. So basically fit potentials to quantum data, then we could get rid of this van der Waals issue, for example. We could go to generative models for making smarter sampling, like not randomly throw stuff at the wall, but really try to fit in the right places stuff that actually fits. And we can go to batch processing and actually use modern hardware to just parallelize the crap out of it. So the question is then, why not just take all these ideas, just throw it on classic tools? So first problem is all these tools, and I guess everyone here who knows a bit about the chemical or like simulation science knows they're built for Slurm clusters in the 90s. They are not at all designed for GPUs. The whole data model is not built around what the GPU likes. There's no native way to plug in any machine learning at all. So like LAMS, for example, supports now some kUPS backend, whatever, but it's a huge pain in the back to integrate it. And usually all of the core code is written in C, Fortran, C++. So iterating on this is probably like 2 years of a postdoc's time, but nothing that you can quickly check out for new ideas. So just no. So what do we actually need in order to make progress here in the pace the current world is moving? So we need native GPU support. We need to put in machine learning as a first citizen into the whole thing. We need very rapid iterations because we just don't know what's the right tool. We just have to rapidly iterate over the stuff. And of course, and this is the hard part, no regressions. Like we can't get slower than normal tools because of the sequentiality. So latency kicks us. And of course, we need to be correct because otherwise we just do wrong science. So this leads over to what tool did we build to address this. The name is called kUPS. So the K has no meaning and the UPS is for Universal Particle Simulator because it's literally the name. And what is it? So first of all, it's an open source library. I will give you the link in the end. So everyone who works on molecules might want to check it out. It's native Python because it's not the best language, but it's a lingua franca and agents love it. And it's built on JAX. Now the question is why JAX? I get this question quite a lot. So one argument is JAX compiles down to the metal. Under the hood, it's an LLVM compiler and basically compiles to native C level. So you get super low latency even for pure CPU codes. You can scale it to a lot of hardware, heterogeneous hardware. You can use sharding. So it means like stuff like domain decomposition and stuff falls out for free. And it's really battle tested because one of the largest companies on this planet built it, develops it, deploys it. So big bet. And there's a philosophy behind. Like what is this tool that makes it different to, let's say, the next LAMS, the next GROMACS, whatever. And the idea that we started off is basically say, any simulation that you want to build is not a configuration. It's a programming language that basically comprises composable operators. So you really want to go a pure mix and match way, like a new custom simulation. It's basically writing something in a language that will compose into a proper simulation. So the idea is always at the core a propagator. So you have some state, and here our state does not only contain particle positions and charges and so on, but literally everything that is stateful, which means simulation parameters, any cache, anything that could potentially change. And then the interface is always all of state, which is totally opaque, totally black box, random key, fed into a propagator, spitting out a new state. So people in functional programming know this is the state monad. So basically the propagator is pure. It doesn't know anything about state. Anything that you feed in is the state and will fold it through the propagator. So what does it mean? It means basically that anything that you can think of in a simulation can be just clicked together. And then I don't dive too deep into the technical parts, but using nice things from functional programming, you can make sure these things click in together like a jigsaw. Whatever falls out of it is correct. Then the other part that we designed is to say, okay, like old school simulation softwares do the classic object-oriented design, and they think more like how chemists or real physicists or people think. But on the other hand, GPUs don't prefer this way of thinking. They just like very fat, flat buffers. So this was the first primitive where we said, okay, everything has to live in one big buffer. So the language has to basically help you to not think about this. So flat data, happy GPUs. So here the idea is basically say like anything is just in a big buffer, the same size. So position charges, to which system it depends and so on. And then you have like one warp that can basically always in a call access operate on one thing. So no blocking, no weird, classic memory issues that you have on the GPU if you do it in a knife way. Question a little bit like, now you have hierarchies, now you have growing needs for semantics, that you have like certain things depend to certain systems, or data is scattered over batches, different systems have different sizes. So how do we solve that? And here the idea is simply that we say we still work in this pure flat buffer system, but we basically work with a lot of different IDs. So which system this depends on is like just one way of saying it, but you could also say molecule idea could be anything that you came up with yourself. So bring your own semantic basically. And then we make sure this is basically just foreign key or database story, foreign key lookup to basically link the foreign keys in the right way to always get this coalesced buffer and still maintain your hierarchy. And the GPU doesn't see anything else than just flat buffers. So the result is that you can then run a lot of different simulations or even connected simulations all on one GPU. And they can have like very different atom sizes. They can have like all, for each system that you run, have like different temperatures, and you collect statistics among them and so on. So you can just do this now. And this, of course, like stuff that is impossible to achieve in any classic software. So now we have ML in the loop, because now if you just want to have machine learning, generative model, whatever, it's just another propagator. If you want to have a new sim, because you have all these primitives, actually with Claude, this is just cooking it up in an afternoon. I could literally just now dump a PDF in there and say, hey, using the tools, compose this, and test it multiple times for stuff. It pretty works out of the box. And you still maintain the full performance. So right now, we're still catching up with LAMs, but I think for floating point 32, for example, we overtook LAMs already in terms of speed. We'll give some numbers for this more. And of course, you keep the full accuracy, because it's still actually very precise in terms of the algorithms. So promised numbers. So for example, for GCMC, the default tool there is Rasper, which is a legacy tool, which is very much battle tested, but just on one GPU, we can get like 50 times the throughput. So it's not like, basically not per step performance, but basically you can just run a lot more stuff on one chip, and it gets much cheaper compared to like running a lot of CPU nodes. Then this is just comparing to ACE, or not to LAMs or whatever, because ACE is usually used for all these machine learning force fields, and there we can get like quite some speed up over ACE if we run, for example, UMA force fields or Maze force fields on ACE. And then, what we also could show that we can easily, for the GCMC part, where the moves are cheap, run thousands of chains on just one L4 GPU, which is very cheap. And then this is like from our release in April. We built this together with NVIDIA. So Ian Buck from NVIDIA was basically saying we can go now from thousands of simulations in the same time to millions with the kind of same costs. So now, after pitching our tool, I want to go through the actual, back to the question, what is the bet? So I would argue agents will write most of the code, including the scientific one, including ours. And I mean everyone here. Just will have no way around. And now going back to this quote. So are we just becoming a Claude wrapper, everyone? And I'd say it's lost. It's in the how. So the classic vibe coding picture, I guess everyone heard about vibe coding a lot, is you basically say, let the LLM roam freely, and then you say, make no mistakes, and you play this big whack-a-mole of getting thousands of solutions that don't work, and just hoping, like with enough tokens and going back and forth, you will get there. But in practice, you have an exponential error surface with every component. The amount of errors you can get is basically exponentially increasing, and you just play whack-a-mole against something that is bound to be fail. So everything that's small works. Once you go to this kind of composable simulation thing, just forget about it. And it's really built in the problem. Like, it's really because it exponentially grows in terms of what can go wrong. And the alternative I would like to present, and that's my kind of opinionated pitch here, is we could also think about it designing grammars, like thinking about designing languages of things where each component we understand, that are well tested, and we know they will click into each other, because then we talk about a whole exponential closure of possible programs that are correct and fast and do their job. And every step on its own can still be tested, validated, and designed. And now the argument, why is this the right thing for agents? And this is like my very scientific 2x2 chart here. So the idea is basically that humans are really good in translating any sorts of vague ideas, specs, whatever, into something like code and basically muddle through. So we don't need everything explicitly written out. We are not working like compilers. We can get like semantic ambiguity and translate it into things that work. What we are really bad in is, and everyone who programmed some Haskell or like worked with C++ templates and so on knows it. Once you go to the very formalized dependent type deep abstractions, it gets really a pain in the butt, and then iterations become slow, not because the tools are wrong or like the things are right. I mean, Haskell programmers preached this since the 80s. It's mostly because the abstractions become too complex for most human brains to actually operate on that very quickly. So this is why often you jump to some pragmatic solutions and you have like this crapbacks of large objects with thousands of fields that you want to override, and you have like, let's do everything just JSON and Markdown because it's easy to think about. But it's mostly because we are not good in traversing a big jungle of the right abstractions. And the agents on the other side, they are really great in just jumping to the conclusion. I mean, everyone who worked with Claude 4.8, for example, observed this. So they're really great in just jumping on any vague spec, but then playing the whack-a-mole and getting them exactly where you want them is the hard part. On the other hand, agents really thrive with abstractions. They don't have any problem at all to dive through 10,000 layers of abstractions. For them, it's easy. For us, it's hard. So I wouldn't say Dario Amodei or like this anonymous Anthropic guy. And I don't think they're right. I think they have a point, but the point is basically the synthesis of both. I would say thinking about a grammar is the agent-native way. How we design it, that's on us. So what I see as a vision is basically on the left, we are humans. We design individual components. We think about how to test them. Maybe the code itself is also written again by Claude, but like the spec for each single component is that we can validate. That's on us. And then once we have those, an agent has a toolbox to very quickly traverse thousands of possible programs out of this, like the exponential closure, out of this start that we just know will be correct. So the question is then a bit like, where's the moat? Like we always talk like these days in European security, talk about like what can we offer? We don't have the data, we don't have the models, like what's still left for us, kind of. And here I would basically let's say the opinionated ideas like models come and go. And we saw the whole story with Fable and so on, like they can just turn it off. So I think always betting on the next LLM will fix it. It will just be better. It's wrong for many reasons. Like one is the whack-a-mole game, but also of course because we just already see it's difficult. What I think is the domain knowledge that stays, and that's a big moat. It's like also like if you think about what's the specialty of certain companies, of certain research orgs, it's like really specific ideas and knowledge that you own. So the question is a little bit, how do you translate this into a language that an agent can traverse? And it doesn't matter whether it's an open source model, whether it's the next release of OpenAI and Anthropic, you become independent of that because at the end the substrate is what you own. So build a language, own the language, and then let agents roam it freely. But it also means the classic application in the usual sense. I would say it's dead. You don't need it. You need a library that an agent can compose from. You don't need to write any end-to-end application anymore. So, and an example for this would be kUPS, or maybe still in the make, but this is at least where I want to have a concrete proof point for this philosophy. And this is where I want to leave it now, and maybe open questions, discussion, is where I say something that's very old school and called that, and people say, why do we even need this? Basically, people who design languages, who design grammars, who think about classic compiler design. I believe people who now use this knowledge to encode any sorts of custom domain into a grammar that is agent amenable. I think these are the people building the future. So I'm very convinced. Yeah. So thank you. And from here on.
Yes, thank you very much, Jonas, for your interesting talk. And yeah, I guess it's an interesting debate which you opened, and I'm also glad that you think that we are not useless yet. So let's continue the debate. So please, questions? Yes, please. You can choose.
Okay, let's maybe wait for the mic on.
Thank you.
Thank you so much for the talk. I will argue that most of what you presented is solving the engineering side. It's like 50x, etc., speeding up the simulations. And I wanted to ask if you would also reflect on how AI changed how you do science, right? When you go to material science, quantum chemistry, in some situation, even the mathematics is not all the way solved. And also kind of improving that part will maybe be more than 50x.
Yeah, I mean, so what I presented today is like what's open source and what I can share. I mean, of course, CUSP is much more than kUPS. kUPS is like the thing that me and Nicholas were basically building, and this is open source release. In the general idea of CuspAI, we of course need to do much more. And then of course, like running the molecular dynamics or GSMC simulation is just a tiny part of it. The other part is like, how do you integrate this with labs and synthesis? How do you integrate this even with characterization of materials? So this is like the very expensive and hard to get part. But of course, like you have also like pre-screening. What kind of material classes are even suitable for this part, for which you have to traverse like millions of scientific literature, for example, in a way. And then of course the other part is also the human factor of like, how do you know what's the right problem? Like you have to have people who go to an automotive company, for example, wants to build, let's say, a fuel cell, and then talk with them and figure out like what's their current draft, what's their lab capacity, and then how does it translate into like a scientific problem. I think there's no one-fits-all solution, but I believe that any AI, whatever you want to call it, makes it a lot faster. And this is the whole core proposition that CuspAI is built around. So what we have is like domain experts who do exactly this part of what materials do we need, or like what kind of science do we need to compute here, or what is even the right cascade, let's say, of coarse tools that are wacky to very precise tools, even down to the wet labs. Then we have, of course, people like me who are more on the engineering research from the machine learning side, thinking about how do we actually get the tools to interact so that it's not just like the same university Slurm cluster as in the old days. But then you also have like a lot of partnership management people, which are, in my opinion, equally important, who actually have to reach out to the scientists in a company lab, for example, and together draft a plan. How does this translate into a language that we can traverse in our platform? And it's a hard problem. Like, I don't want to sugarcoat anything about this, but also I believe, as you say, agents help a lot to traverse the search space much, much more rapidly. And it's really, I think this agent, like this agentic search engine, is also at the core of how whole CuspAI operates. And yeah, exactly trying to offload as much as possible to like something connecting all these dots. Yeah.
So maybe more on the technical side, but don't we already have modular toolkits like OpenMM? What's the difference between kUPS and OpenMM? Like, I guess the agent is also able to build a simulation out of it, right?
I mean, I know OpenMM very well. I worked a lot on it during my PhD when I tried to work on Boltzmann generators and make it interact with the machine learning code. It's a huge pain in the neck, to be fair. Because the bigger reason is, I mean, OpenMM was built by design in the classic simulation idea. So you have basically molecules, you have atoms, you have certain integrators, you have certain thermostats, whatever, which are very hard-baked in a certain way, which is great if you want to do exactly that. But once you deviate a little bit, and one example would be you do grand canonical Monte Carlo where you want to move the lattice with MD, but you want to do the sampling with GCMC. So already impossible to do with any of the tools without any machine learning in the mix. It's literally just like taking two different integrators and putting them together. OpenMM wouldn't be able to formulate the whole problem. Okay, you could probably do this. You could, it's C++. You can, as open source, you can write it under the hood, of course. But the iteration time to get there is a whole different story. Here, it's literally just clicking together two puzzle pieces. So my argument is mostly tools like OpenMM, LAMMPS, Chromax, they're amazing for what they did. They were like a monolith, an application bit, which like had one specific goal in mind, and they optimized the heck out of it. So it's very hard to beat them specifically in their game. But once you deviate a little bit from that, you can see how difficult it was to get machine learning into LAMMPS, for example. then it becomes very, very tricky to do anything that is production ready. And that's what we want to solve with kUPS.
So if I want to compose, for example, if I want to use two different force fields, like get up, sorry for the technicality.
Yeah.
If I want to employ like a prior on a force field, that is easy with kUPS.
Yeah, you could say you have two different force fields. One is only operating on the framework. One is only operating on the solvent.
And torch models as well. I can.
Yeah.
Okay.
Like this is like we use JAX, but I mean didn't want to make it full engineering talk, but like we integrate all torch, JAX, whatever. It's like in the same unified way. So it's like basically interoperable. That's the whole goal.
Thanks.
Yeah, thank you for the nice talk. I was wondering more on the product, or rather, maybe rather where experimental validation comes in, or whether you really stop at the pre-screening of some large chemical spaces, and whether it's, because to me that's more of a basic research problem maybe compared to.
Yeah, I think it's a tricky one. So there are, let's say, let me maybe explain it more from a commercial side. So if you go to a company and you say, hey, give me all your data, and then we build a nice foundation model for molecules and sell it back to you, no company will do this. This is like why the usual way of these, let's say the AI paradigm of just gather a lot of consumer data, train a big model out of it, and this is your product, this can never work. Because no one who actually owns the chemistry, does this for 150 years, is like a world expert for clean water or whatever, will ever let you look into any of your data. So you need to, if you want to make it a business that works, you need to think about how to make it work. And then it's much more about integrating with these partner companies in a way that makes sense for them. And one part is, for example, they already have certain lab capacity. They already have certain things they are really good in. The question is like, what is the part that is a challenge for them? Often it can be something that is on the modeling side of saying, okay, we thought about this idea, but we could never really exercise this because we are lacking the tools to even, and the people to even just iterate on that. So they stay basically stuck in the local minimum of, let's say, taking some version of a solar cell, some version of a semi-manufacturing process and just iterating on this, getting better. But they see that something fundamentally should be done different, but they can't do it themselves. And this is basically where we, from this, could say from the outsider with our own platform, that's basically our IP is the mode is basically this platform that we are building, then can basically dock into this thing and together. So this is not like just a 2 days thing. This is like months to years partnership. Help them to actually accelerate this process to look, for example, there could be new molecule classes, like material classes to look into that could have like similar purposes, but we have to research them. For this, we have to do certain simulations. We have to speed up these simulations. We have to figure out first, like, how do they already fit into the landscape? So you can do this, of course, with a 200 people research team and years of research. Usually people don't do it. With CUSP, we try to condense the process into few people doing this with a lot of automation.
Thank you.
Are there any more questions? I have to.
Hi, I'm just curious because, so to say, we're more and more relying on well-crafted agentic systems to write large infrastructure for our code. And basically in the history of science, there was this remarkable example also with the weather prediction. So in the beginning, there was this belief that if we increase the capacities, like if we increase our tools, the quality of tools, we're going to get better and better predictions. But at some point, we realized that the underlying system is chaotic and there is this butterfly effect and there is a fundamental limitation for predicting the weather. And here also we kind of have this accumulation of error, fundamental blow up, and there is this idea that AI will going to write 100% of the code. But I wonder if it could be also some sort of a fundamental limitation that this accumulation of error is chaotic and human it will be always needed to control the operations.
I mean, you don't even need a human here. You could also go to just very simple thing like if you look into density functional theory or like really one step lower, look into actually solving the stationary Schrödinger equation. You can just prove there's no other way than doing the hard part, which is NP hard, to actually find the ground state. And now, of course, you can assume maybe that if the LLM saw enough ground states, I mean, how? But that it maybe learns how to extrapolate. But even if you believe that, it means the computations that the LLM has to do somewhere in its latent space cannot be more efficient than what you can do on a computer normally, because otherwise it wouldn't be an NP hard problem. So I think they're like very simple fundamental parts in this physics where it's very clear these can't be offloaded to, or they can't dream that they will be somehow dreamed up. So that's for sure. So it's also my argument why certain things stay hard and need to be encoded in your whatever grammar it is. The other part, and this is, I think, I would like to challenge a little bit. So, for example, AlphaFold is a good example. So the argument that protein structure prediction will not be solvable just from a pure computer. And this was made for decades. Actually, when the whole CUSP prediction was made up, it was like really saying, this is a hard challenge, people will not solve it. Now we have something that solves it. Now, of course, you can come up with all sorts of rebuttals and saying, okay, for this specific thing, it still underperforms, or there's like some noise in it, whatever. True. But still, you could say, for any kind of pre-screening nowadays, at least any medical or pharmaceutical research lab that I know, it became a backbone. Like you would not try, like you would not jump to anything else before trying this first, and then maybe you can see, okay, iterate from there. Which also tells you, even if like certain tools are not perfectly precise, or like they work on a different theory level, or they're like clearly having a model assumption, connecting between the models, for example, going from quantum level to fluid dynamics or whatever, that's always was the hard part in science. And I mean, I don't know what's your background, but if, for example, look into randomization theory or whatever, then you can say, okay, it works perfectly on like funny little lattices. But once we do this on atoms already, it becomes a huge research field. Like Cecilia Clemente at the FU is, for example, doing this for a whole career, how to go from atoms to something like more coarse-grained. It's super hard. And I would argue this is exactly this fuzziness, this bridging between models, between real-world applications, between very confined computations that are extremely expensive. So you need all of them, but the fusion of it, that's the hard part. And this is my strong belief where anything AI, agentic, machine learning, whatever, this will just make it work.
Scale bridging.
Sorry?
Bridging scales.
Yeah, bridging scales, bridging models, I would even say.